This will be the lecture on section 1.1 from college algebra in context. The objectives of this section will be to determine if a table, graph, or equation defines a function, find the domain and the ranges of functions, do a scatter plot from a set of ordered pairs, use decimal notation to evaluate functions, and apply real-world information use in a mathematical model. We'll start here with a set of data. And you can see these are degrees Celsius and degrees Fahrenheit and the equivalents. The inputs, these are sometimes referred to the x and y values if we're using ordered pairs. The inputs will be, in this case, the Celsius values. They will be -25, -15, -10, 0, 30, 60, and 100. The outputs then will be the y values, or the Fahrenheit temperatures, -13, 5, 14, 32, 86, 140, and 212. We did these as ordered pairs. We would start out with -25, -13 would be an ordered pair, -15 and 5 would be an ordered pair, -10 and 14 would be an ordered pair, etc. And the next thing we're going to do is graph those ordered pairs. You can see we have graphed these ordered pairs as they go along. Now you might notice that they appear to be pretty much in a line. That this is called a scatter plot, where you just graph the points, the ordered pairs. You'll notice these appear to be in a line. And in fact, right here we drew the line through them. So we have this ordered pair as a line, and it turns out this is the equation. Given a C value, a Celsius temperature, we can use this equation to find out what the Fahrenheit temperature would be. So this then would become a function. A function, this is important, is a rule or correspondence that assigns exactly to each element in one set called the domain. Those are the ones we begin with. They were the Celsius temperatures in our last example. Exactly one element in the second set called the range, or Fahrenheit temperatures. So each Celsius temperature matches with one Fahrenheit temperature. A function can be a set of ordered pairs, the data we just had, a table, a graph, an equation, or even a verbal description. So it can come in a variety of forms, and we need to be able to identify them. Now suppose the child's normal temperature of 98.6 degrees Fahrenheit, and the only thermometer available is Celsius, indicates the child's temperature is 37 degrees Celsius. Does this reading indicate the child's temperature is normal? Well, first we'll use the equation we have. So we'll plug this in. So the Fahrenheit temperature equals 9/5 times the 37 degrees Celsius plus 32. 9/5 times 37, well, the 9 times 37 will give you 333/5 plus the 32. Well, 332/5 comes out to be 66.6 as a decimal, plus the 32, that added up is our 98.6. That would degrees Fahrenheit. So does the reading indicate the child's temperature is normal? Yes, it does. Now the independent variable, that's the one, almost you could say pick out of a hat. These are the inputs, often the x values, and they are defined by the domain. The independent, these are the ones that you're just given. You are given these, or you pick a number. That's the independent variable. The dependent variable, this is the outputs. They're called dependent variables because what they are, the value they have, is dependent on what the x value started with. Okay, sometimes they're the y's. Sometimes we'll see decimal function notation of f of x. These are the range values, and they are based on the given independent variable. In general, domains are all real numbers, unless you're given some restrictions that you start with. Sometimes that will be fine. Or other things automatically have restrictions. Functions with variables in the denominator may have input values that give 0 in the denominator. So find the values not in the domain. Here's a place where we would have restrictions on the domain. If we had a function that had something like 3 over x plus 2 as part of the function, set the denominator equal to 0. So x plus 2 equals 0, and that x would equal negative 2, and this wouldn't, then for the function x could not equal negative 2, because that would make the denominator of fraction 0, and we cannot have that. Another case where domains are limited, functions with variables inside an even root may have one or more input values that give negative values inside the even root. So if you had a square root of x plus 3, if we had an x value that would make this negative, we could not have that. So you set the expression inside the even root greater than or equal to 1, or greater than or equal to 0, and solve for that. So you say x plus 3 greater than or equal to 0. So x has to be greater than or equal to negative 3. That defines the domain. Now here we're given some graphs, and we have to, with the functions, determine the domain and then the range. Okay, the domain here. The domain is the x values, and of course the x-axis is the horizontal axis, and we just have part of the graph. We would say these go on forever. So the domain, the x values would continue forever to negative infinity and infinity. So we could say the domain here from negative infinity to infinity, or we could say the domain was all real numbers. Now the range, remember the domain is the x values. The range are the y values. Which y values work? When we list them, we go bottom up. So you can see that this graph starts at y equaling 0. So the range here, 0 is a point, so it would be 0 to infinity. Or x has to be, y has to be greater than or equal to 0.